So let's begin. Well, you do know that a computer system is made up of software, data, hardware, communications, and people. So these are the key building blocks of a computer system. Without all these components being there, a computer system is not complete. You do know that what hardware is and what is software. Data is a very essential part of any computer system or information system these days, and it is the data that we actually input into the system. It gets processed in a certain way, and then certain outputs or results are produced according to the user's requirement. Communications is another very important or integral aspect of any computer system or information system. And without communications being there, the whole idea of computing cannot be realized these days. People, another very essential or important entity. People like you and me, professionals, students, we are the ones who actually make use of these computer systems or information systems on a day-to-day basis to get certain useful tasks done out of these systems. In order to understand how a computer system is built up and how it works, it is often divided up into subsystems. This division can be shown using top-down design to produce structure diagrams that demonstrate the modular construction of the system in a diagrammatic form. Okay, so well, uh, if you look at all the components, and we had to sort of choose two of the most important building blocks of a computer system, we can easily say that they are actually hardware and software. Hardware, we do know, has its own divisions in terms of input devices, the processing devices, and the output devices. But the other very key component of any computer system is the software. Software is actually that part of any computer system or information system, which is the driving force of the computer system. And we can easily say that without the software being there, the hardware alone just cannot do anything. So it is the software or the programs that you install on the computer hardware that makes it do various things or perform various tasks. Now, when softwares are produced or when they are created, we do know that a top-down design approach is usually used in order to effectively design any particular computer program or software. And what is the top-down design? Top-down design is basically dividing the whole program or the whole system into sub-modules or sub-programs just to understand the program or the system in a better way. Now, if we look at this example of an alarm app, we did discuss it earlier as well in our first lecture. That let's assume that this alarm app is part of a particular larger program or software. We can take the example of a mobile phone. A mobile phone performs many tasks for you, and it has many programs in it, and then those programs have sub-programs. So if we consider that the alarm app is just one of the programs in our mobile phone, and we have to devise an appropriate and effective alarm app or an alarm program for our computer, how for our mobile phone, how can we go about it? So uh, following the top-down design approach, we can divide this alarm app program or system into various subsystems or submodules. For example, initially we can divide it into set alarm, check time, sound alarm. These can then further be subdivided into more submodules or more subprograms, you could say. Now, if you look at this structure diagram, we can easily see that as we go down, more detail is added to the program, and we can sort of look at it in more detail. If we divide it into submodules, uh, it makes it easy for us to not only understand the whole program or whole system in a better way, but it is also it also becomes easy for us to accurately or correctly design it or design the program so that it functions properly. So, this is what is known as the top-down design or the modular design approach, where you devise a solution to a problem in such a way that you divide it into submodules or subprograms. As you go down from top to bottom or top to down, there's more detail added to any system or any program in terms of its subsystems or submodules. And it is these subsystems or submodules that then make it easy for us to focus on each and every little aspect of the program in detail so that we can devise a detailed, effective solution. Okay, so continuing from here, our next topic is basically what is an algorithm. So let's see what algorithms are. An algorithm sets out the steps to complete a given task. This is usually shown as a flowchart or a pseudocode. Now, the term algorithm is used to describe the set of steps or tasks which are usually performed in a sequence in order to accomplish a certain task. This task may be a large task or a larger problem or a bigger problem, or it may be a small task or a small problem. It doesn't matter whether it is a small problem or it is a big problem. The idea of an algorithm is to ensure that you write down the proper steps in a certain sequence in order to devise the working or the solution of the task or the problem at hand. And the two major tools or techniques that are used to accomplish a successful algorithm are flowcharts and pseudocodes. So let's see what are flowcharts and pseudocodes. A flowchart shows diagrammatically the steps required for a task or a subsystem and the order that they are to be performed. So if you look at the right here, a flowchart is a diagrammatic or a pictorial representation of devising a solution to a problem. It consists of certain symbols or shapes. You can see here that there are certain symbols or shapes. We will have a look at what these shapes and symbols basically mean a little later in our topic today. But for the time being, just have a look at how a diagrammatic or pictorial representation of an algorithm looks like in the form of a flowchart. Pseudocode is a simple method of showing an algorithm using English-like words and mathematical operators. So, another technique or a method that is used to write an algorithm is pseudocode. And pseudocode is written in the form of simple English. You make use of simple English words to write down the steps or the instructions in a certain order or a sequence in order to devise a solution to a problem or in order to write down the steps that are needed to accomplish a certain task. Now let's focus on what are the different steps or stages which are essential in producing an algorithm. Make sure that the problem is clearly specified. So to begin with, the most important thing is to make sure that you understand the problem properly. You understand what the problem is, because if you do not understand the problem that you have at hand, then you will not be able to devise a proper solution for it. So the first step is to ensure that you understand the problem properly. Break the problem down into subproblems. Most problems, even the simplest ones, can be divided into input, processing, output of results. So we do know that this is the cycle that is usually followed by the computer as well to deal with various problems, be it a simple problem or be it a very complex problem. The method that is used by a computer to solve that problem is to divide the problem into inputs, processes, and the outputs. So when you do that, it becomes easy for you to separate between the various sections or the various parts of solving the problem. You identify the inputs, identify the processing parts, and then you finally identify the outputs that need to be produced out of the program or the system. Decide on how any data is to be obtained, stored, processed, and displayed. So, how the data is to be obtained, what data needs to be input, how that data has to be obtained, how the data is to be stored, where the data is to be stored, how the data is going to be processed, and how the outputs are going to be produced or displayed from the system or the program. Decide on how you're going to construct your algorithm using a flowchart or pseudocode. So here you also need to decide which uh, problem solving technique you're going to make use of in order to devise the solution or construct the solution to the problem. You can make use of flowchart, you can also make use of a pseudocode. But what usually is done these days is that people who write computer programs or devise basically initially conceive a program and then write down the solution to the program. They usually make use of both of these techniques. They make use of flowcharts as well as they make use of pseudocodes. Construct your algorithm, making sure that it can be easily read and understood by someone else. So make sure that whether you make use of a flowchart or you make use of a pseudocode, you have laid it down properly. If it is a flowchart, make sure that the symbols have been used correctly, because all the flowchart symbols have a certain meaning. They are placed in a proper logical order, and they have been annotated correctly. They have been correct annotation has been used on them, which is easy to understand also for even a novice, so that anybody who looks at the flowchart is able to easily read through, look at the logical flow of the flowchart, and it is easy for him or her to understand what the flowchart is actually trying to depict. Same goes with the pseudocode. A pseudocode written in the form of simple English-like statements must make use of the correct words, the correct technical terms, if any. We will have a look at a few technical terms which are usually part of a pseudocode a little later in our discussion. But whatever the instructions are, make sure that those instructions are clearly defined and they are written in a proper sequence. It is very important to follow the logical sequence of instructions. Use several sets of test data to find any errors. Now, this is a point that we would sort of emphasize upon a little more, or look into a little more detail later on as we discuss more things in this chapter. But for the time being, I can only tell you that whenever you devise a solution to a problem, or you design a computer program making use of either a flowchart or a pseudocode, in order to test the working or the accuracy of the solution, you can always test it by making use of certain dummy test data. Now, that test data can be just any data, that hypothetical data that you can think of, that you can make use of. You just put that data into the algorithm, make it run through the algorithm, and produce certain outputs or results. And it is through this method that you can check if your algorithm or your program is working properly and it is producing the kind of results that you are actually looking for. Now, this process of making use of test data and making it run through an algorithm is also known as dry running. So we will have a look at how algorithms are tested, making use of test data and the dry run technique to see how effective your algorithm design is. If any errors are found, repeat the process until you think that your algorithm works perfectly. So, one more benefit of making use of test data to test your algorithm is to check that the data when the data is run through, it produces the kind of results that you're actually looking for. And if it does not produce the kind of results that you're looking for, then this means that there is something wrong with the way your algorithm has been designed or your solution has been designed. Then you would have to work on the design of your algorithm, be it a flowchart or a pseudocode. There might be something that you have not placed incorrectly in a logical order in your design. So you can just sort of go back to the drawing board, design your algorithm again, try to identify the problem area, and then retest it with the test data. So you keep on doing this until unless the algorithm starts producing favorable results or the kind of results that you think that the algorithm should actually be producing. Okay, now let's have a look at some basic examples of flowcharts, or you could say the flowchart symbols and what their meaning is. Now, these are the basic symbols that are usually part of any flowchart. Let's have a look at all these symbols and what they mean. This kind of a shape, it's sort of an elongated rectangle, but it is rounded at the edges. This kind of a symbol is used to depict the start and the end of a flowchart. And then this elongated rectangle with the properly defined edges, this symbol is used to depict the processes or the processing that goes on into any algorithm or into any program. Then this diamond shape is used for decision. Decision is where a flow chart may branch off uh, into two areas. A decision is where usually a condition is tested. Whenever a condition is tested, it may result in the condition being true or the condition being false. Now, if a condition is true, then you branch off from this diamond shape and you may perform a certain task in case the condition is true. And in case the condition is false, then you may branch off into something else and you may perform something else or some other task. So usually a diamond shape would always branch off into two areas. Then this parallelogram, this symbol is usually used to depict the input and the output of data from a system. This shape, which looks like a rectangle, but at the bottom it has this curved line. This is used to display a document or a report. Usually a hard copy document is shown, or a hard copy output which is being produced from your program, from your flowchart, is usually shown through this symbol. Then this rectangle that has these two parallel lines is used to display or show a subroutine. Now, what is a subroutine? A subroutine might be, a pre-stored module or a pre-stored program that performs a certain task or a certain set of tasks in the overall larger program. So that is what a subroutine is. And then, of course, the arrows depict the flow of logic. So the direction of the arrow actually shows the flow of the logic or of the program. That what is happening first, where is the program branching off from one point to the other, and then to another part. So the logical flow of the working of the program is depicted through the use of these logic flow arrows. Now, you can look at an actual description of how a flowchart looks like. I'm not going to get into the detail of what this flowchart is depicting. I will use this as an example a little later in today's lecture, but the idea of showing it here is to show you how all of these symbols or most of these symbols are used to construct a flowchart. Let's now have a look at some basic examples of some basic examples from everyday life as they are depicted by making use of flowcharts. Let's have a look at this first example. Uh, there's a process here, you could say. Well, you can always add a start symbol from at the top here. You can always do that you start, and then you are encountered with a process that says lamp doesn't work. So if the lamp is not working, what do? You check if the lamp is plugged in. In case the lamp is not plugged in, no, then you make sure that the you plug in the lamp. In case the lamp is plugged in and it is still not working, check if the bulb is burned out or not. In case the bulb is burned out, then, in case yes, then what is it that you would normally do? You would replace the bulb so that the lamp starts working. In case you do know that the lamp is plugged in, this is yes. Bulb is not burned out either. Okay, it is not burned out. Then, uh, you know, uh, you simply switch on the lamp and it keeps on working. So, if you look at this particular these particular symbols, as I told you earlier on, we see the processes. We also see this diamond shape, which is usually used for decisions, okay, and they are conditional, and they always branch off into two areas. This condition could either be true or it could be false. In case it is false, what do you do? In case it is yes, what is it that you do? Now, one thing that you can always uh, be mindful of is that it is not necessary that the yes and the no outcomes from a decision or from a diamond would always branch off into a process. Sometimes they might branch off into a process, checking off something else or performing another process or a task. And at other occasions, they might simply branch off into another condition that needs to be tested. Okay, so it is not essential that both these branch off into processes or into tasks. So this is something that you need to remember. Let's have a look at another example. This is the one that you actually saw on the previous slide. So start, login. This particular flow chart is depicting the process of logging into a system. We can sort of take the example of an ATM machine here when you have to withdraw cash using an ATM machine. And you do know that when you have to withdraw cash from an ATM machine, you have to first insert the card and then you need to identify yourself by putting in a PIN or a personal identification number. And only upon authentication can you actually further carry on with certain other tasks. For example, you can only withdraw cash in case you have been authorized as a legitimate or an authentic user of the card. So let's see how this kind of a flow chart depicts that process. So you start, you log in. The first thing is to see the first thing that is seen is that is are you authorized? In case you are not authorized, then you are allowed three attempts. You put in your PIN first. If it is not identified or it is not a legitimate PIN, you can be given another attempt and then another attempt. And then on the fourth attempt, you would simply not be allowed to enter into the system because the internal check of the system is such that it would only allow you to enter a PIN three times. And if you do not get it right, then its internal security check is that it would not allow you to carry on any further attempts because it may be taken as a situation where maybe it's a stolen card which is being used by somebody and the person is just using a hit and trial method to get into the system or to make use of the card. So the internal security mechanism would not allow you to have more than three attempts if you get your PIN wrong three times at a trot. So in case you're not authorized, you are provided three attempts. And in case you're authorized, then of course the access is granted. And once the access is granted, then of course you can perform various activities on an ATM machine. We do know that other than the fact that you can withdraw cash, you can do certain other things, or you can avail certain other services as well with ATMs these days, such as you can pay your utility bills, your electricity bill, you can top up your mobile, you can ask for a mini statement, and just so on. So you can perform any particular task once you have been authorized as a user, as an authentic user. And in case you exit module, the exit module is doing what? Once you are done with what you had to do, you just simply exit, and now you are ready to start again if you want to. In case you do not exit, then you can just perform another. If you perform one activity, you can just perform another activity using your ATM card. All right. So this is how, through a simple flow chart, you can display the working or the process of an ATM machine, which is a real life system. Let's have a look at this common example as well. So you start, is it raining? In case yes, then you find your umbrella, because if it is raining, you will look for your umbrella because if you have to go out. Um, so if you have, yeah, you look for your umbrella, find umbrella. Have you found your umbrella? No. Is it raining? Find the umbrella again. Okay. If you have found the umbrella, yes, bring umbrella, take it, and then just go out. All right. And right at the start, it says, in case it is not raining, okay, then you do not simply have to bring umbrella and just you can simply go out. You have to perform all these checks or go through all these tasks in case it is raining. That you have to look for umbrella, and if you have you keep on looking for the umbrella till you find it. Once you have found your umbrella, then you can simply take it, bring umbrella, and you can go out. In case it is not raining, you can simply go out without the umbrella. Okay, some more, a little different examples. Okay, start, input temperature or read temperature, and then the condition, is the temperature less than 32 degrees Fahrenheit? In case it is less than 32 degrees Fahrenheit, in case this condition is true, then you simply display it is below freezing. All right. And in case the temperature is not below 32 degrees Fahrenheit, okay, in case no, then you simply display it is above freezing. So another simple module that can make you check or make you display a certain type of output based on condition being tested. Another example, start. As you do know that this parallelogram is an input output symbol. M1, M2, M3, M4. Now M1, M2, M3, and M4, say for instance, are marks for 4 different subjects. You input these marks, and then you do what? You add them up all together and you divide them by 4 to find out an average. Now this is a process. You could see that this is a rectangle, an elongated rectangle, which is a symbol which is used for processes in a flow chart. So if we look at this process, what is being processed? All the marks are being added and they are being divided by 4 in order to find out the average. Whatever average is found out of these marks, that average is being assigned to, you could say, a variable called grade. Well, I hope you do know that what variables are. You do make use of variables in mathematics, in physics. Variable is just a container of a value, and the value that a variable contains may change while it is used for a certain activity or task. So you can just keep that in your mind for the time being. We will be focusing on variables later on as we do more topics in programming, but for the time being, you can just simply understand what I've just told you about variables. So for the time being, you can assume that whatever average is calculated is being assigned to a variable called grade. Now here in a condition, you are testing the grade, the value in the grade. If the value in the variable grade is less than 60, you check, is the value in this variable grade less than 60 according to whatever has been found out here? That value is contained in grade. Is it below 60? In case yes, then you print fail. And in case this condition is false, okay, it would branch off into a no. You would simply print pass. So and then you simply end. So that is what this little module is showing. This particular program is depicting by making use of a flowchart. So you could see that by making use of a pictorial representation and formulating the logic of the working of a program pictorially by making use of flowchart, since we do understand the meaning of the symbols as well, we can easily devise the solution to a given task or the solution to a problem or a system. Uh, Pictorial representation makes it very easy for even novices to look at something and understand what is it that is being explained or what is it that is being depicted. So, uh, in today's lecture, what we have seen is that how we can make use of algorithms which can be created or which can be written by making use of flowcharts as well as pseudocodes. Flowcharts are a diagrammatic or pictorial representation of the working of a process or a task or a program or subprogram. And we have seen through various examples how this pictorial representation uh, actually displays the logical flow of the working of a program and how these flowcharts are used to devise the solution to a problem or to a task or a subtask. We haven't focused on pseudocodes in today's lecture, but as we move on in some of our lectures in future, we will be focusing more on pseudocodes as well. So that is all for today's lecture.